Well, we're now reaching the end of Chapter 4 of James Stewart's calculus textbook. Chapter 4 is on applications of differentiation. And in these last section, we begin to do some problems. Of course, we've been doing examples, but this section, the sixth section of this chapter, are called optimization problems. And we're doing a lot of examples of how the application of differential calculus to various areas. Probably the most important theoretical, element in this section is what's called the first derivative test. So the first derivative test is a test to tell you whether something, what an absolute minimum or an absolute maximum of a function is, which is a very important practical thing to know. We're going to call these absolute extreme values. Extreme meaning maximum or minimum, and absolute means it's the maximum of all the maximums, so to speak, of the function, or the minimum of all the minimums of the function. There are local maxima and local minima, but we're talking about absolute maximum and absolute minimum. Okay, so say that C is a critical number. What's a critical number? Well, a critical number is basically where you have a function and you've taken the derivative of that function and you set it equal to 0. What is the significance of this? Well, the derivative is 0 when the slope of the tangent to the function is 0. And the slope to the tangent of a function is 0 when that function is either at a maximum or at a minimum. It's a turning point. And so the critical number tells you that something is either a local or an absolute maximum or minimum. So say C is a critical number. Now let's say that this function, this derivative function, is positive, which would mean that it's going like, or let me do it so that it looks the right way for you. Let's say the function has a positive slope when x is less than c. But then when x is greater than c, it has a negative slope. You see? Positive slope, negative slope. So what is that going to be? Think. What is that turning point going to be where it goes from a positive slope to a minimum slope? It's going to be a maximum, right? That's going to be an absolute maximum. It's going to be absolute if for every x is less than c, it's positive, and for every x is greater than c, it's negative. That makes sense if you think of the graph. By the same token, if the derivative function is negative when x is less than c, especially for every x is less than c, and then positive for every x is greater than c, then it's an absolute minimum value. So this is the biggest theoretical takeaway. This is the thing to take from this section more than anything else. Then he does, of course, some examples. So I just picked one of the examples. Here's example 5. What is the largest rectangle? So here's a rectangle. What is the largest rectangle that can be inscribed in a semicircle, not very well drawn, of radius r? In other words, from the center, the origin, to anywhere. By definition of a circle, the radius is going to be the same from the origin to any of the semicircle. Okay, so we know there are two truths, two equations that we can write on the basis of the situation here. So the area of this rectangle, which is what we're trying to find the maximum, right? We're trying to find the largest rectangle, the maximum value for the area of this rectangle. The area of a rectangle is the height times the width, so the height is y, and the width is going to be 2x. We have 1x here, and then we have another x here. So the area of this rectangle is going to be 2xy. Now we also know that the equation of a circle is in the general form x squared plus y squared equals r squared. So we've got two equations here. And so if we substitute x for y, so let's take this equation of a circle. We know that y is going to be, we rearrange it, we minus the x squared on this side and then take the square root of it, and so y equals that. We can substitute that back into our other equation. Remember, area equals 2xy. So area equals 2x this. Okay, great. Now, If we take the derivative of it so that we can find the critical number, the point at which there's a zero slope, so we're going to do the first times the derivative of the second plus the second times the derivative of the first. For whatever reason, Strong does it the opposite, but that's the way I learned it. So the first times the derivative of the second, there's the first, 2x, times the derivative of the second. So this is r squared minus x squared to the 1/2 power. So the derivative of that is going to be r squared minus x squared to the negative 1/2 power. So that's why it goes down into the basement. When you have a negative power, it goes into the denominator. And then, of course, we have to take the derivative by the chain rule of the stuff inside. And so the derivative of negative x squared is negative 2x. So that's where this negative 2x comes from. Okay? So the first times the derivative of the second, plus the second times the derivative of the first. So the second, there's the second, times the derivative of the first. And the derivative of 2x is just 2. Okay, now we got to do a little simplification. So the way we get from here to here is we multiply this by the square root of x squared minus the square root of r squared minus x squared over the square root of x squared minus the square root of r squared minus x squared over the square root of r squared minus x squared. That's multiplying by 1, right? And what that does to this is this top one becomes simply r squared minus x squared, and then we now have a common denominator. So that's how we get the common denominator. And then we got to simplify a little bit. So negative 4x squared plus 2r squared minus 2x squared. And so we're going to end up with minus 4x squared and 2r squared. We can factor out a 2 then. R squared minus 2x squared. So here is the derivative of this function here. Okay, so when is this going to be 0? Well, this is going to be 0 when the when the top numerator is 0. And when is the numerator going to be 0? The numerator is going to be 0 when r squared equals 2x squared. In other words, when this equals this, then the numerator is going to be 0. So when r squared equals 2x squared, that's the critical number. So we solve for x. And what we do is we solve for x we divide by 2, so that's how the 2 gets in the denominator. And then we take the square root, that's where the square root came from. So when x equals the square root of r squared over 2, that's when we're going to have the maximum area. So what is that largest area? Well, we just plug it back into to this equation here, a equals this. Plug it back in, and what do we get? We get blah, 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 which reduces to r squared. So the maximum area for a situation of a rectangle inscribed within a semicircle is r squared. Okay, they do tuck in at the end of the chapter some business and economics, and so I'm just going to go through the terms and leave it at that. So we encountered the cost function in chapter 3, I believe it is. Cost function is simply a sum function that tells you what the cost is going to be per unit sold, and that's x is the number of units sold. So marginal cost is the derivative of the cost function. The rate of change of the cost is called marginal cost. I haven't quite gotten my head around why they call it marginal cost. It seems like it would gel better with my brain if they'd have called it something else. But hey, ours is not to question why. Ours is just to memorize or die. And so the marginal cost is the derivative of the cost function. It is the rate of change of the cost per unit sold. Per unit, that is, per unit. The demand or price function is the price per unit. So if x is the number of units sold, yes, x is the number of units sold, then the revenue function is going to be the number of units sold times the price per unit sold. That makes sense, right? Units sold times price per unit sold cancel, and we're left with price. So that's the revenue function. Tells us how much money we're making. Well, not exactly, actually. That's telling how much money we're taking in. So the marginal revenue function is the rate of change of the revenue function. Okay, the derivative, how much we're bringing in. So the profit function, this is how much money we're making. The profit function, P of x, is going to be the amount of revenue we're bringing in minus the cost per unit sold. So P of x equals R of x, revenue minus cost. That makes sense. Profit equals revenue minus cost. Yeah, I can deal with that. Now, as you might expect, there is a marginal profit function, which is going to be the derivative of the profit function, the rate of change of profit per unit time. Okay, so here's some business economics terms in relation to calculus. So there you have it, optimization problema. Problemas. Sorry for my Spanish.